layout, performance, and all that much faster than before. And not only that, in general, it helped me write better application code as well. So I'm kind of hoping that it will have the same effect on you guys as well. And last but not the least, browsers are these amazing, advanced, black boxy, magical tools that we have all based our careers on, right? To know how they work under the hood is just absolutely freaking awesome. So, which is why this talk is here. Before we start the journey, I would like to peek into Chrome's architecture from 10,000 feet so that we get along with the most important components that are out there. First, there is one and only one process called the browser process. It is responsible for the UI of the browser, right? Things like the tab strip, the address bar, the navigation buttons, and all that. And browser process creates a bunch of threads, like the UI thread, there is a network thread, and then there is a storage thread. And there are many other threads as well. Then there is a renderer process. For every tab that you open, the browser process creates a new instance of a renderer process. The responsibility of the renderer process is to render the content of the page on the screen, which is why Blink, the rendering engine of Chrome, and V8, the JavaScript engine, they run within the renderer process. And renderer process creates a bunch of threads as well, like the main thread, which is where Blink runs. And there are other threads like Compositor thread and raster thread, and we'll get into the details of these in just a little bit. Another thing to know about the renderer process is that they are actually sandboxed. So they cannot make direct system calls. They cannot access network directly. They cannot access file systems directly. So in order to be able to do that, the render process has to go through the browser process, which justifies the existence of network thread and storage thread in the browser process, right? And this communication happens between the browser process and all the renderer processes using Chromium's inter-process communication systems. The true responsibility of making graphics layer commands to put pixels on the screen lies on a separate process, and it's called the GPU process. And it has one and only one thread, the GPU thread. All right, now that we have the general understanding of the major components of Chrome, we can start the journey. And the journey starts with the user typing in the URL in the address bar, like this. First thing that Chrome does in response to this is to figure out the IP address for this domain name, right? The process called the DNS resolution. In order to do that, the network thread in the browser process is going to first check Chrome's own DNS cache to see if the IP address is in there. If it's not in there, it's going to talk to the operating system. If it's not in there, the OS is going to talk to your router. If it's not with the router, the request goes to your ISP, Internet Service Provider. If it's not in there too, the ISP is going to make a recursive query to different name servers until the IP address is resolved and it makes its way back home to Chrome. Now Chrome has the IP address of the server that it needs to connect to. So that's what it does in a process called TCP connection. If DNS resolution is like finding out a phone number of a person, establishing a TCP connection is like actually making the call, right? So just like when you make a call, you start by saying hello to each other. Chrome and the server are going to do the same thing in a process called the TCP handshake. And it works kind of like this. Chrome's going to send a packet, a SYN packet to the server. Hey, server, let's synchronize. And the server acknowledges that by sending an ACK packet back, acknowledgement. And then Chrome's going to send acknowledgement to that acknowledgement again, right? Full server round trip. This is Chrome and the server saying hello to each other. Now that they have established the connection, Chrome's going to send the actual GET request to get the content from the server. Server is going to generate that content, index.html or whatever HTML. Let's say that HTML is about 45 kilobytes large, right? The server is not going to send the entire 45 kilobytes back to Chrome. It's only going to send 14. Why? Because TCP, the protocol, is built this way. TCP does not know how big a bandwidth there is between the server and the client. So to figure that out, it starts small by sending a small amount of package. And that size is 14 kilobyte. Why 14? Because every TCP segment, probably not readable, but every TCP segment has a payload size of 1460 bytes. And TCP always starts with 10 TCP segments, which amounts to 14 kilobytes. And once the server receives the response for these 10 TCP segments, it's going to double the amount of that and send 20 TCP segments. And this process continues until a certain limit is reached or until the server delivers all the content to the browser. Now the important takeaway here is TCP always starts slow. No matter if you're on HTTP 1 or HTTP 2, and no matter what kind of bandwidth you're on, the first server round trip is always going to be capped to that 14 kilobyte. So if you want to serve content, important content to the browser as soon as possible, that's why there is this best practice. Put that in the first 14 kilobyte. Then you're going to get that content in the first server round trip. Better, inline that above the full CSS. The styles for the content that is visible to the user immediately. Inline that and put that in the first 14 kilobyte. And the browser has everything that it needs to render the content as soon as possible to the user. That's the fastest we can render. The only way to render faster is to actually bring the servers closer to the browser. See, TCP is a very paranoid protocol, right? There is a running joke, like if there are two people who are trying to tell a joke to each other in TCP protocol, then it kind of goes like this. Like the guy goes like, hey, I would like to hear a TCP joke. Hello, would you like to hear a TCP joke? Yes, I would like to hear a TCP joke. Okay, I'll tell you a TCP joke. Okay, I'll hear a TCP joke. Are you ready to hear a TCP joke? Yes, I'm ready. See, it goes on and on because TCP is very paranoid, right? Because it's built to serve content reliably over a highly unreliable channel. So it has to constantly confirm. And there's a lot of back and forth involved. So if you have important content, put that in the first 14 kilobyte, and then it's going to be on the first server round trip. Now, there are several other steps in the network stack, like setting up an HTTPS connection, for example. But I'm going to skip that to keep the focus on rendering. So let's say that the HTML starts streaming to Chrome. The browser process's network thread is the first one to start receiving that HTML, right? So the browser process is going to create a new renderer process and ask it to render the page. And all the raw bytes of HTML is going to be streamed to the main thread of the renderer process. Now we enter the blink territory. This is where the real rendering pipeline starts. And the first phase of the rendering pipeline is to parse the HTML. All these raw bytes of HTML, they are converted into characters based on the character encoding specified in the response headers. Those characters are converted into tokens. And using those tokens, C++ objects are created that represents each and every HTML tag in the document. And like all these tags are structured in a hierarchical order in the HTML, all of these objects are structured in a tree-like structure, which we call the DOM tree, right? A thing about this HTML parsing to create a DOM tree is that JavaScript can block this HTML parsing. So if you have a script tag like this in the head of the document, so there's just a script tag, Blink is going to parse the HTML until it sees the external script. Then it's going to download that script, parse it, execute it, and then continue further with the parsing of the HTML. Now, most of the time, JavaScript is there to just add interactivity to a page full of content. It should not be blocking the rendering of that page. Which is why there's a best practice in the industry to put the JavaScript at the bottom of the page. Because if you do that, all the HTML will be parsed, and the content will be progressively rendered by Chrome, and then JavaScript is going to be downloaded, parsed, and executed. There are better ways nowadays to download JavaScript. For example, if you use async attribute with the script tag, the download of JavaScript happens parallel to the parsing of the HTML. The thing with async script is, though, it does not respect the order in which the scripts appear in the document. As soon as the async script comes to the browser is going to parse and execute it, no matter how they appear in the document. So if you have order dependencies between your scripts in the document, the better way to do it is using defer attribute. Because if you use defer attribute with your external script, they're going to be downloaded parallel to the HTML parsing as well. But the order of the scripts is going to be respected by the browser when it's parsed and executed. Now there is a new thing in Chrome. What Chrome does is, like, if there are scripts larger than 30 kilobyte, Chrome is actually going to parse it on a separate thread, parallel to the download of the script. And that is great for performance because your parsing of the script is going to be finished like milliseconds after the download. And not only that, it's going to bring the parsing out of the main thread. There's already a lot going on in the main thread, as we'll see later. So it saves a lot of space in the main thread as well. In the same way, CSS is said to be render blocking. What does that mean? If you have a link to an external style sheet like this, Chrome is going to parse the HTML, render content, all good. But then as soon as it sees the style sheet, it's going to download that CSS first, block the rendering, which is why CSS is blocking the render, while JavaScript blocked the parser, and therefore the rendering as well. And only after the CSS is downloaded, it's going to render the rest of the content, which is why there is the best practice in the industry to put the CSS at the top of the document. We need to ship that style sheet as soon as possible to the browser. Better yet, like we saw before, inline that critical CSS so that we do not incur this additional network trip. Better yet, put it in the first 14 kilobyte, then you have everything in the first server round trip, right? And then you can load the rest of the CSS in an async way. What does it mean to load CSS in async way? It means to load the style sheet in a way that browsers do not block rendering because of it. And unfortunately, we don't have an async attribute that we can use on the link tags, but we do have a little workaround, and it works like this. Basically, you need to apply a different media to the link style sheet. In this case, we're applying print. So if the browser sees like, hey, this style sheet is not made for screen, then I'm not going to block the rendering. And when the CSS is actually loaded, then we're going to set the media back to all. In that way, the style applies to the document again. This is the simplest, most cross-browser way to load CSS asynchronously right now. But anyway, after parsing all this HTML and creation of the DOM tree, the next step in the pipeline is to figure out how each of this node is going to look like. The process called Recalculate Style. In order to do that, Blink is going to use the style sheet that we gave to Chrome and its own internal user agent style sheet, and then traverse through the DOM tree to figure out, to compute this style for each of these DOM node. Computed style is basically a giant map of all the CSS properties that are out there and their values. And this is created for each and every DOM node. Now that we know how each of the node is going to look like, the next step in the process is to figure out where they're going to end up in the viewport, in a process called layout. In order to do that, Chrome is going to create a separate tree called the layout tree, and it only contains the DOM nodes that are actually visible in the document. Notice that the head element and the meta elements are no longer present in the layout tree. In a similar way, if you have display none some of the elements, they wouldn't appear in the layout tree either. And then Chrome is going to traverse the layout tree, adding geometry data to each of the node in the layout tree. Geometry data are things like the x and y coordinates and the width and the height, right? Now we have a tree of DOM elements where we know how each of the element is going to look like and where they're going to end up on the screen. So we can go ahead and paint them. Paint happens in two stages. In the first phase is just recording paint operations, not actually painting. So for example, for HTML, we need to draw a rectangle. For body, we need to draw another rectangle. For a paragraph, we need to draw a text block. Kind of like the Canvas API that we know, right? So Blink is going to just collect these paint operations for every element in the layout tree. And the execution of these paint operations to actually create the bitmap happens in a separate phase called the rasterization, where all these paint operations are executed to create this bitmap, and this bitmap is uploaded to GPU as textures. But like I said before, the renderer processes are sandboxed. They cannot make direct system calls. So they cannot make direct graphics layer commands as well. So all of these GL commands are proxied through the GPU process. Now we have the code that is now present as pixels in the GPU memory. Let's do a quick pipeline recap. We started by parsing the HTML. Then we've created a DOM tree, and we figured out how each of the node in the DOM tree is going to look like in the process called recalculation of style. Then we created a layout tree and figured out where each of the node is going to end up in the viewport in a process called layout. Then we collected the paint operations for each of those nodes, executed those paint operations in a process called rasterizations to create bitmaps that we uploaded to the GPU memory using the GPU process. But unfortunately, things are not as quite simple as this. See, Blink has to do this over and over again because things changes in the page that we have, right? So things can change in the page because user may scroll content, user may pinch to zoom, there may be animations happening, or maybe JavaScript is doing some stuff to change the state of things in the page, right? So if Chrome has to do the entire rendering pipeline every single time something updates on the screen, like every single time somebody is scrolling, then we can blow off the frame budget quite easily. But what is the frame budget? Most of the screens that we have nowadays have 60 Hertz refresh rate. Like the talk before, it's going to 120 as well, but most of the screens that we have now are 60 Hertz, meaning the screen refreshes 60 times per second, meaning the operating system is going to ask Chrome to ship a new frame, to create a new bitmap 60 times per second. That means if things are scrolling, for example, in the page, Chrome has to create 60 different images every second. That's a lot of work to do. If we zoom in a little bit, to create every single frame, we only have 16 milliseconds really. So if Chrome was to do the entire rendering pipeline for every single frame, and then one of these pipeline stages takes a little bit longer time, then we have missed the frame. And this is what the users perceive as a stutter in the movement, which we call jank. Mind you, all of this is happening in the same thread where JavaScript is executing as well. JavaScript is a highly performance sensitive area, and it can easily make us miss a couple of frames. And it only requires a couple of missed frames for users to perceive the jank. So in order to prevent all of this, in order to prevent the main thread from being the bottleneck in rendering, Chrome works with the concept of layers and compositing. What are layers? What is compositing? See, if you have a page like this, and there are two elements in there, and they are animating over each other like this, Chrome has, if you were creating a single picture, single bitmap, Chrome has to basically recalculate style, layout, and paint every single frame to create this new bitmap, right? So every time this is moving, there's a new frame that needs to be generated. That's a lot of work. So Chrome, instead of doing this, it splits the page into multiple layers. And instead of doing the layout, repaint, and all that every single time, it's just going to talk to the GPU directly. Like, hey, GPU, you have these 3 different bitmaps. Just move them over each other, please. I don't need to do anything on the main thread. That's layers. And the fact that they are composited on top of each other to create the last actual image of the page, that's compositing. So let's see how the layers and compositing actually works. Remember the layout tree? Layout tree was the tree where we knew in every single DOM node how the DOM node looked and how where they appeared in the viewport. Chrome is going to split that layout tree into another, surprise, surprise, tree called the layer tree. Now, by default, there is a layer created for the root node of the document. So HTML and all of its children automatically belongs to one single layer. But if you're using CSS like wheel change transform or 3D transformations, you can bring any element and all its children into a separate layer. Now, instead of collecting paint operations for one layer tree, Chrome is going to collect paint operations per layer, right? Now, this information, the layer tree, is all that we need in Chrome to be able to ship a new frame. So what's going to happen is like Chrome is going to give all this information to a separate thread, a different thread than the main thread, called the Compositor thread, in a process called commit. Now, Compositor thread owns all the information that it needs to render the page. So the actual rasterization, like creating bitmaps out of the paint operations, happens via the Compositor thread. And it does this parallel. So if there are 2 layers to be rasterized, it's going to create 2 raster threads, and it's going to rasterize the content there. So now we created 2 different bitmaps for 2 layers. So some of the layers are really big, and it's kind of wasteful for CPU and the memory to be rasterizing the whole content, right? So to not do that, to do things efficiently, Compositor also breaks a layer into tiles. And it only rasterizes the tiles that are actually in the viewport or closer to the viewport. This saves a lot of memory and the CPU consumption. Then the next step in the process is for the Compositor to actually create GL commands, the graphics layer commands, to put these different layers together to create the final image for the page. That is called the Compositor frame. And then this GL command is given to the browser process. And browser process is going to do its own composition. It's going to add the browser UI, right, around the Compositor frame. And then finally, browser process is going to issue the GL commands that we collected via the GPU process to put the pixels on the screen. So there's a lot that happened. Now we finally have pixels on the screen. So let's recap the pipeline one more time. So we no longer have the simple pipeline like we saw before. We have the renderer process, which has the Compositor thread, rasterizer thread, and the main thread. We have the browser process, and we have the GPU process. When we're loading the HTML for the first time, we're going to parse the HTML, create a DOM tree. We're going to calculate style for each of the DOM node. Then we're going to figure out where each of the node is going to end up in the screen in the process called layout. Then we're going to create different layers from that layout tree. we're going to collect paint operations for each of the layer, and then we're going to give all this information to the compositor thread as a commit. Compositor thread is going to chunk these layers into smaller tiles, and then it's going to rasterize those different layers into bitmaps using raster threads. And once it receives all the rasterized layers, compositor thread is going to generate GL commands to composite all these different layers together to create a final image of the page and give that GL command information to the browser process. Browser process is going to add its own UI on top of that compositor frame and give that information to GPU process and tell GPU process to draw and put the pixels on the screen. So that is the entire pipeline that happens in Chrome while rendering the HTML for the first time. But what about the updates? What if JavaScript changed some things? In that case, see, the main thread is where a lot of things happen, but compositor thread is really the boss. And as the boss, all the input events, they are first proxied through the compositor thread before it even reaches the main thread of the renderer process. So the input events are collected by the compositor thread. And if it cannot handle it by itself, it's going to forward that to the main thread of the browser. This is where JavaScript comes in. JavaScript is going to handle that input event. And let's say that you did like request animation frame, or you changed the layout of the object, or whatever, you dirtied the DOM. Then the main thread is going to ask the compositor thread, like, hey, something changed, so let me know when I need to start creating a new frame. And compositor thread, being the boss, also is synchronized with the refresh rate of the screen, which we call vsync. And compositor thread, when it knows about, hey, the vsync is happening, so we need to ship a new frame to the operating system, is going to start the process of creating a new frame. That's going to come down to the main thread, and main thread is going to kick off the rendering pipeline. It first does that by calling the request. It does that by calling the Requestanimationframe callbacks, and then it does the entire pipeline that we saw as before, creates the layers, does the paint and everything. Now, the important thing to notice here is like Requestanimationframe callbacks are called as close to the screen refresh rate as possible. Not only that, it's called right before the entire rendering pipeline of Chrome. So that if you're doing animations and if you're changing things in the DOM, Requestanimationframe is the best place to do all of those work. Now, we have collected paint operations for each of the layer. All this information is going to go to the compositor thread. Compositor thread is going to do the same thing as before. Prepare tiles, rasterize to create bitmaps for each of the layer, and then it's going to give that information to the browser process. Browser process is going to put the UI on top of that, go to the GPU process, ship the pixels on the screen, right? But why is this compositor thread architecture important? How does that make a difference? See, oh, by the way, so if there is still some time remaining after the rendering pipeline and before the new frame needs to be generated, then that's where the requestIdleCallback is invoked. So if you have some like non-critical work that needs to be done in JavaScript, requestIdleCallback is the best place to do it because it does not affect the rendering pipeline, right? So again, why is it all important? How does this help Chrome? Basically, let's say when things are scrolling, right? Compositor thread receives the scroll event first before the main thread, and it doesn't even need to go back to the main thread because compositor thread has the layer tree. It has all the information it needs to create a new frame. So it won't even go to main thread. It's going to just rasterize new tiles if necessary, and then just directly talk to the GPU. Hey, just translate the content by the amount the user scrolled the page. No main thread involved at all. And this is possible because compositor thread has all that information. This is where it becomes useful. So even if JavaScript is heavily being used during a scroll, Chrome is going to scroll content as smooth as it can be. But watch out. Chrome can scroll this content smoothly even when main thread is busy. But if you have code like this, where you're adding touch event listener, because JavaScript can actually prevent the touch event, it can prevent the scroll. So Chrome the compositor thread has to come to the main thread and ask like, hey, are you gonna prevent the scroll? And then the main thread is gonna be like, no. So if we do this, basically we are bringing the scroll back to the main thread. So in order to prevent that, you have to use passive event listeners. And in order to use passive event listener, you basically have to add this third argument, passive true. Basically, passive true is telling Chrome like, hey, Chrome, I promise I won't cancel touch events, so do your scroll on the compositor side, right? In the same way, if you have GPU accelerated animations, if things are animating in the browser, compositor thread is going to just like not even go to the main thread, just apply new transformations, make those GL commands directly to the GPU process, and we're done. So animations will be hitch-free because it never has to come to the main thread. But again, watch out, because all the elements that are actually animating, they need to be on a layer of their own. And we learned that already. In order to create a new layer, you can use CSS property like will change transform. But not all CSS properties can be animated just by the compositor. Actually, there are only 4 CSS properties that can be done on the compositor side. Opacity, scale, rotation, transition. That's it. If you're animating width and height, it needs to come to main thread. Anything else, it needs to come to main thread. So for example, try to only animate on 4 of these properties. So if you're animating height and width, try to use scale instead. If you're blurring the background, maybe create blurred version of the background already and just change the opacity. If you're moving top and left, use a 3D translation. You know, there are tricks to put your animations in only one of these 4 properties. But also, watch out. If you create lots of layers, they're going to take a lot of memory, especially in the video memory. And if you're on a memory constrained device, that can be very bad for your device. So watch out for the layers. So actually, that's all the information I had to show you guys how the code that we write gets converted into pixels. There's a lot of things that's happening in there. Hopefully it made sense. But to sort of nail it down, I have created a demo. And we can also check in Chrome DevTools how all the things that I said are shown in the DevTools. So let's go ahead and do the demo. How much time do I have, actually? Ah, that's enough. Let's see. So I can do it more even. Yes. Is this readable or terrible? It's okay. We can live with this. Okay. So there's a simple page here. And we are basically loading the script on the top of the document. Bad practice. And it actually takes 1 second to load this script. It's a slow loading script, right? So let's go and see how this works in our Chrome DevTools. I think I got to bump it up as well. So I'm going to start recording, and I'm going to load that page. Let's stop it. All right. Woo, that's a very less space over here. So what I wanted to, maybe I can zoom it out a little bit. What I wanted to show here, I think I need to undock it into a separate window. That's probably a bit better. I need my network. Okay. So over here is where we start getting the HTML, right? So let's go ahead and see. This is where the HTML, the parse HTML, the first step that we saw, right? Parse HTML to create the DOM tree. It's happening right over here. But if you come down here to the summary, you will see that we only parsed line 0 to 3, not the entire thing. If you go in here, you will see 0 till line 3. I think there's a bug in Chrome that it actually shows a line count to be 1 less than the real line count. It should be 1 till line number 4. So as soon as the script is seen, it's going to stop parsing of the HTML. This is the parser blocking behavior of script, right? So that's over there. And then it's going to download the JavaScript over here. You can see up here, the script is being downloaded. Let's go all the way when the script is downloaded. And then the parsing of the rest of the HTML happens. You can see that down here. Line 4 till -1. -1 being like end of the document. So this demonstrates the parser blocking behavior of JavaScript. We don't want this, which is why we need to put this scripts at the bottom of the page, right? Also notice, before the JavaScript is downloaded, the frame that is shown is still the old tab. The browser is not going to show the content immediately because it is being blocked on JavaScript. And once the JavaScript is actually downloaded back here, then you're going to see that the content is actually displayed, right? So which is why JavaScript goes at the bottom, but like we saw before, you can actually do it async. So let's see how this page changes when we do it async. What we learned was if we use async script, the parsing is going to be parallel to the download of the script, right? So let's see if we can actually see that happening. So HTML gets downloaded down here, parsing of the HTML. And instead of parsing only the first 4 lines, we are parsing line number till line number 18. So we are downloading the script parallel to the parsing. This is why async is super important, right? Not only that, even before the JavaScript is actually downloaded, which is right over here, we are already showing the content, right? So this is why we need to use async. And the other thing that I talked about was if there are scripts that are larger than 30 kilobytes, like Moment.js is pretty large, so let's go ahead and use that. Let's start a capture for this. That should be good. So we're going to download that script, Moment.js, over here. But if we go down a little bit, you're going to see a separate thread being used to actually parse that script. And this is happening parallel to the download. So this is also an important thing. Like if you have this like lots of script that you're shipping, like Facebook has a lot of scripts, but they are able to use this different threads out of the main thread to parse a lot of them actually in this way. So Chrome does a lot for us in this manner. So that's the first demo. Let's go to the second one. Actually, just to the, I have a simple page here, just shows hello world, right? Let's go through the entire process of this page. So I'm just going to create a capture. And hopefully I'm able to demonstrate the entire process to you guys. Oops. Huh? Just disappeared. Not just disappeared, it froze. Let's try one more time. All right. So let's try to go through the entire process. We have parse HTML. What did parse HTML do? Basically create the DOM tree. After the parse HTML happens, we're going to recalculate the style, right? To figure out how each of the element looks like. That's what appears in the Chrome DevTools as recalculate style. Then we're going to figure out where each of the DOM node is going to go in the viewport in a process called layout. That's how it appears in DevTools. And then we're going to collect down here, we're going to create a layer tree from the layout, like basically chunk the page into separate layers. That's what's happening over here. And then we're going to paint. Paint is basically collecting paint operations, not actually executing it, right? You can actually see that down here in the paint profile. Like if you go here, you can see the paint operations that Chrome is collecting. It's like clip rect, draw text block, kind of like Canvas API, right? You can see exactly what's happening. Like if you execute it like this, like, oh, okay, the draw rect happens, so this gets painted, and this gets painted, and all that. So this is the painting phase, initial painting phase. And once this painting phase is done, we're going to ship that information to the compositor thread, right? So this is what's, when you see composite layers in Chrome DevTools, it's basically, it's badly named, basically. It should be called like commit layers, because that's what is actually happening. So it gives all this information to the compositor thread. Compositor thread is down here. It exists on its own. And the compositor thread is going to receive that layer. The next phase in the process was to rasterize all these different layers. And it uses a separate thread, you can see it down here, raster thread, to rasterize the paint, right? Multiple threads being used to raster. And once those pages are rastered, it eventually is going to go to the GPU process, which you can see down here. And GPU process is the one that puts the pixels on the screen. All right. You can also see that if you have, like, for example, now let's skip that. I'm just going to go to the next demo. Now let's look at the demo for animations. Like see what happens in DevTools when things are animating. So I have another page here. Let's go to the page. Basically what happens is like if I click on it, it starts moving around, right? So let's see what happens in DevTools when I actually do this. I'm going to put it here, DevTools over on the left. And going to go to the performance panel. Start recording and gonna click on it. Boom. Animation happened. That's enough for now. So I'm just gonna capture it. So a lot of things happening over here. Probably the click event happens somewhere over here, right? So click event happened over here, and then we call the request animation frame. Request animation frame is basically telling the compositor like, hey, we're gonna probably need to create a new frame, so let me know about it. So that request goes to the compositor thread where it's notified like, hey, we're gonna have to start shipping a new frame, and let main thread know about it. Later, when the vsync interval hits, we're gonna do exactly that. Compositor is gonna start the new frame process. Then it's going to, in a separate stage over here, you can see, it's going to request the main thread to create this frame. That request is going to come to the main thread over here. The main thread has to start creating a new frame now. First thing that it does, callback for the animation frames. All of those are executed. Hits the entire rendering pipeline or recalc style, layout. We've seen it 100 times till now. Ships all of those information to the compositor thread, and the compositor thread is the one that actually is going to rasterize content using multiple raster threads that you've seen, and like we've seen before, put the pixels on the screen. This is the whole back and forth that's happening between the compositor thread and the render thread. Now, as we saw, I may take a couple of minutes more. As we saw, like the main thread is like extremely busy here. So we are using CSS animations, but still the main thread is doing a lot of work. So in order to check that, actually, if I hog the main thread for like 5 seconds, it will just stop. The animation is being affected. That means that we are doing this animation on the CPU side, not on the GPU. That's bad. So why is that happening? We see, if we inspect all of this single frame, we will see that we're actually doing paints, layout, all those things every single time, and that's bad, right? So let's see if we're actually painting. You can use DevTools to actually show paint flashing rectangles. If you use this, DevTools is going to show you exactly what's being painted. So every single frame, we are painting all this content. That's no good. But we have learned stuff today, right? So we're going to, like to animate things on the GPU side, we know that we have to put it in a layer of its own. So let's go ahead and do that. We're going to use wheel change transform to put that animating element into a layer of its own. I'm going to reload the page, hide the paint flashing for now. And actually, you can visualize these layers in multiple ways. You can go to this menu over here, go to more tools, and then rendering. And then there is this flag called layer borders. If you use that, Chrome is going to show you all the layers that are present in the page by surrounding it with this yellow-orange border. So if there's a border around an element, that's a separate layer. And you can see these like cayenne colored borders as well. These are the tiles, the layers that are broken down into smaller tiles. Yeah. And there's another way to visualize this as well. That's using the layers panel. When you use the layers panel, you can exactly see like, oh yeah, cool. So we got 2 layers, right? So that's 2 layers. So we are heading in the right direction. So when this animating happens, it should actually just animate this 2 layers using GPU. Is that what's happening? Let's go ahead and try it out. I'm going to hog the main thread again. Still doesn't work. Why not? Well, we learned another thing. When we animate, to be really able to use the GPU accelerated animation, we need to use either transform, opacity, rotate, or scale, right? But here we are doing, well, animating left and left properties, which is no good. So let's go ahead and change those into transforms instead of left and see if that affects. Let's reload the page. We are probably still having multiple layers, all cool. And then we're going to start animating it. Then we're going to hog the main thread. The main thread is hogged because this blue is, still remaining blue. But the animation is still happening, 60 frames per second. So now, these are the ways you can really, debug animations, debug rendering issues, and go towards the right direction to see what's exactly happening. And Chrome DevTools is a really awesome tool to help you get all this information. If you really want to look into the guts of the browser, the Blink, V8, and all that, go to Chrome Tracing. That is going to give you a world of information. So yeah, guys, that was pretty much what I wanted to share with you guys today, the whole pipeline of how Chrome converts code to pixels and how you can use that information to have better animations, rendering, performance on the applications that you write. Thank you very much.